All right, class, this is part 2 of 8B problems. This is number 60. For the elements in the third row of the periodic table and beyond, the octet rule is often not obeyed. What factors are usually cited to explain this fact? Well, it's actually pretty simple to explain. Take a look at phosphorus as an example. There we go. So take a look at phosphorus as an example. We know that the Lewis dot diagram for phosphorus looks like this, but why does it look like that? Well, if you take a look at phosphorus, phosphorus is argon. Where are we at here? Neon. There we go. Neon, 3s2, 3p3. So if I look at my orbital diagrams for that, that means I got my 3s here, and I have 2 electrons there, and then that's a really big orbital. So I got 1, 2, 3 for 3p, and I got 1, 1, and 1. Remember, they spread out because they repel each other. Now, you would normally look at this and say these 2 electrons over here are not going to bond at all because they're already together and they don't have room for bonding. However, okay, this is my fancy dotted box to show that there is room here for other electrons from other atoms to bond. Okay, I don't like the way that looks, so I'm just going to try and do this over again. So 1, 2, 3, that's a 3p. So each one of these orbitals has room for bonding, which means that phosphorus can bond 3 times. However, we know that from electron configurations that there is a 4s, and we're going to ignore that. Actually, I should put that up above the 4s. Let's see if I can do this right. But there is also, after the 4s comes the 3d. Now the 3d is like this reservoir of spots for electrons. So that means what phosphorus can do is it can actually bump up to 5 bonds because one of these electrons will move over here and find a spot in the 3d. So that means that now I have a 3s spot, I have 3p's spots, and then 1 3d spot like that. Okay, this is called a hybrid orbital. Now the 3d still has, there we go. The 3d still has 4 other spots that are unoccupied. So if we have something like pf5, I hate it when it does that. I want to show you this. This is fun, isn't it? Isn't this fun? There we go. So I got PF5, and if the F I use in green like that to show that the bonding electrons from the F fit in here, 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 and here, that means that I have 1s, I have 3 p's, right, orbitals, and 1d, sp3d. So this is a hybrid orbital. I'm previewing chapter 9 a little bit, but it's all part of the same concept. So yes, that means that phosphorus then, even though I'm going to draw this in green, can have a bond here, 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 and here. Although it doesn't quite look like this because it's 3-dimensional and I'm drawing on a 2-dimensional board. And you don't need to know exactly what it looks like just yet. That's chapter 9. So phosphorus PF5, this is an expanded octet. The reason why it expands is there's room in the 3d orbitals to take on some extra electrons. Okay, moving on. Describe the molecule chlorine dioxide using 3 possible resonance structures. Well, so this is ClO2. ClO2 means that I have 1 Cl. That's going to look like that. I have 2 oxygens. That's going to look like that and like that. Okay, so let's see what we can do. We know that this is going to get a little bit messy because I have 7, 6, and 6, which means that 13 and 6 is 19 electrons. We have an odd number of electrons. That's not good. That's not stable. Chlorine is my central atom like this. So one of the things we can do is we can put the single electron on chlorine, and then we're going to have to double bond and double bond to oxygen. The reason why I say that is because I know oxygen is stable with a double bond, like this. So that means chlorine has the expanded octet, obviously. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons, which is odd. So that is one thing that we can do. There are other things that we can do. Let's see if we can figure out what else we can do. I'm always thinking that instead of a double bond, 2 double bonds for chlorine, we may go to a single bond and use what's called a coordinate covalent bond. Coordinate covalent means that chlorine is giving both electrons to the bond with oxygen. So if I do something like this, at least this oxygen is, that's going to get us closer. That gives chlorine only 9 electrons and 6 assigned. Okay, so that might be a little bit closer to what we're doing. You could do that on both sides then. So it's really just about, here, I'm going to back up and do this. Follow along with me. And do this, and we got 2 coordinate covalent bonds, and then it just depends on where the extra electron is, that single electron. So sometimes that single electron is on chlorine, sometimes it's on one of the oxygens, like this, like that. So in this case, it's over here on this oxygen, and then if I flip it around, I can do the same thing over here, like this, oxygen, like that. And then there it is on that side. So these are 3 resonance structures. There's the single electron there it is there, and then here it is on the chlorine. Do any of these resonance structures satisfy the octet rule for every atom? No, that's impossible. You can't satisfy the octet rule for every atom so the answer is definitely a no, and that's because there are an odd number of valence electrons. Okay, so you can't have octet rule satisfied when you have an odd number of valence electrons. It just doesn't work that way. Mathematically, it's an impossibility. Why or why not? Okay, so the answer is no, and the why or why not is because you have an odd number of electrons. All right, let's move on. I'm going to show you an example using the formal charges select a resonance structure that are the most important. So I'm going to go back to here. I'm going to go, you guys, formal charge looks like this. I'm going to do it very quickly. I got valence electrons and assigned electrons. I got 6, 7, 6. Okay, I need to get rid of this stuff right here. That's going to be 6, 7, 6, 6, 7, 6, like that. We're going to do this quickly. Assigned are 1, 2, 3, 4, 5, 6, 7. That's a -1. Assigned are 1, 2, 3, 4, 5. Okay, that's a +2. Whoa, that's unusual for a plus or -2. And then that's 1, 2, 3, 4, 5, 6, 7, like that. So that's 7. That's a -1. So that does all add up to 0, but this +2 right there that's going to be a problem. So here I got 1, 2, 3, 4, 5, 6. This one actually works out to be 0. I got 1, 2, 3, 4, because we break that, 5, 6, so that's a -1. And this one is 1, 2, 3, 4, 5, 6, 7, and that's 7. That's a +1 bonehead. And then that's a -1. Okay, so there's one. So resonance structure number 1 is not as stable as number 2. So it looks like it's going to be, because this is going to be 7, this is going to be 6, and this is going to be 6. So this goes to 0, this goes to a +1, and this goes to a -1. So either of the second ones, so either one of these, second or third, let me answer here. So that means that second or third resonance structure is stable, at least more stable, okay? So most important, 66, so this is a good one. So notice that what we're going to do is we're going to use bond enthalpies. I'm going to add up all of the bonds I have on the reactant side, which means before the arrow. So reactant side, I add up all those bonds. This will go pretty quickly. I got 3 bonds that are CBr bonds. That's those. So that is CBr bonds. I don't know how much that is yet. So 3 times that, I have a CH bond like this, and then I have a Cl-Cl bond. So just one of those, Cl-Cl bond, like that. I'm going to add those up, and I'm going to subtract them from the amount I'm going to do after the arrow. So that means I have, again, 3 CBr bonds like this, plus I have now a CCl bond, CCl bond like this, plus, and now I have an HCl bond, just one of those also. So I add these up as I go, and then I simply subtract the 2 of them, and that gives me my answer in kilojoules per mole. So where do I get that information from? Well, here is where I get that information. One of them was 413. One of them is, or 3 of them times 276. And what else do we have here? Carbon-carbon, 328. Okay, and then I have an H and a Cl and a Cl and a Cl. Where's my Cl and Cl? Right here. Okay. Oh boy. So I'm going to have to flip back and forth to add these in here. So this is going to be, oh, poop. I might as well. The CBr is 276. 276, okay. Let's remember that. So 3 times 276, the C and H was 413, and Cl and Cl, what was that? Cl and Cl is 242. Oh, a palindrome. Okay, 242. Okay, so what I do is I add that up. Let me grab my calculator. When I add this up, like this, I got 3 times 276 for the first one. That's 828 plus 413 plus 242 gives me 1,483. Good. This is still 276. The CCl bond is 328, and the HCl bond is 431. Okay, so 328 and 431. So 3 times 276 equals 828 plus 328 plus 431 equals, and then I get 1587, like that. So I subtract the 2 of them, and I get a negative 104 kilojoules per mole. And that's how I do that. It's very simple. Add up all of the bonds before the arrow, add up all the bonds after the arrow, and then subtract the 2, and that's how you get it. So it would be, let me just make sure I didn't screw that up. I'm pretty sure I got that right. You may have to add up. Yep, that's it. Perfect. Reactants minus products gives us a minus 104 kilojoules per mole. Okay, do the second one just like that, and the third one just like that. Okay, and we'll check it then. I went through that pretty quickly, so I'll answer problems in class. We're on a Zoom. All right, class.